Hey there, today we're going to talk about a parallel circuit. The definition of parallel is a circuit that has more than one path for current to get to ground. In this case, the current has three paths. It can go through R3, R2 or R1. As with a series circuit, the first thing we do is work out the total resistance. But I'm going to do this in a slightly different way to normal. I'm going to make a point, and it's a point you should always remember with parallel circuits, and that is the voltage across R3 and across R2 and across R1 all equal 12 volts. Therefore, from Ohm's law, current is equal to voltage divided by resistance. We can work out each current flowing, and then when we've calculated those currents, we can add them together and get the total current IT flowing at this point. IT will also join back together here. So let's begin. We'll start with the first current here, IR3. IR3 equals the supply voltage, which is 12 volts, divided by the value of R3, 10 ohms. 12 divided by 10 is 1.2. The current flowing through R3 is 1.2 amps. And we will do the other ones as well very quickly. IR2 is 12 divided by 100. It's 10 times smaller, of course, than IR3. The current is 0.12 of an amp. IR1, 12 divided by 1000, will of course be 10 times smaller than the current through R2. When we add all these three currents together, get a total current, IT, which equals 1.332 amps. That's this current here, IT, there. I've got this set up in a simulator so you can see how it all works out. When I run the simulator, the current from the source, the total current, 1.332 amps, flows through each branch. Most of the current flows through R3 because R3 is the smallest resistor, so it allows more current through. 10 times less current flows through R2, and once again 10 times less current flows through R1 than R2. They all join back together at this point before returning to the power supply. The volt drop across each branch in the parallel bank is exactly the same at 12 volts. Now Ohm's law tells us that resistance is equal to V divided by I. Therefore, for our circuit, the total resistance will be 12 divided by 1.332 amps. Back to the online calculator, and the total resistance for this circuit is 9 ohms. We've gone through quite a lot there to prove this. We've worked out the total current and also the currents through each branch. I'm going to backtrack a little bit now and show you the normal way of working out resistance to prove that it works. So normally with resistance we use a technique known as product divided by sum. It only works for two resistors at a time. We take the product of two resistors and divide by the sum of those two resistors, and then we move and take that result and apply it with the next resistor in the bank. So we will start with the R3 and R2. R3 is 10 times 100 divided by 10 plus 100, which gives us 1000 divided by 110. This gives us a resistance of about 9 ohms. We take this 9 ohm value here and apply product over sum with the final resistor in the bank there. And this same technique can be applied regardless of how many resistors you have in a bank. But now we have 9 times 1000, and we divide that by 1009, which is 9 plus 1000, of course. So the total resistance for this circuit using the conventional method is 9 ohms, and we proved that with the current as well. We should note two things. For a parallel circuit using exactly the same resistors as we did in series, the current flowing through the circuit, the total current, is much greater. Therefore the power will be much greater. We can work out power now. Total power dissipated is equal to V times I, 12 times 1.332, which is roughly speaking going to be around about 16 watts. Much more power for a parallel circuit. The second thing you should note is the total resistance, 9 ohms. For any parallel circuit, the total resistance will always be lower than the value of the lowest resistor in the bank of resistors. In this case, the lowest value is 10, and we've calculated 9. If you do a parallel calculation and your value is higher than the value of the lowest resistor, you've made a mistake, and you will need to go back and check your working. That was quite a roundabout way of tackling a parallel circuit with my rubbish graphics tablet skills. However, I hope that you picked up some valuable information during this video and can apply that information when you go to work out your own parallel parameters. Bye bye.